We are going to discuss about Birch-Sponer extrapolation method. This is another method available to find the dissociation energy of the diatomic molecule, in the excited state. Right? For electronic spectrum, or from the electronic spectrum, we can find the dissociation energy of the molecule in the excited state. In the IR spectrum or Raman spectrum, using IR spectrum or using Raman spectrum, we can find the dissociation energy of a diatomic molecule in the ground electronic state. See, Birch-Sponer extrapolation method. Extrapolation method. See, this method is applicable for diatomic molecule. It is applicable for diatomic molecule. Okay. What is the use of this method? Listen. For diatomic molecule, using Birch-Sponer method, we can find the approximate dissociation energy. Dissociation energy, I will put D0. Dissociation energy of the molecule in the ground electronic state. The double prime indicate ground electronic state, and we get the value in wave number. To find the dissociation energy of the molecule in the ground electronic state, we use either IR spectrum of the diatomic molecule or Raman spectrum. So from the result or from the IR spectrum of the diatomic molecule or from the Raman spectrum of the diatomic molecule, we can find approximate dissociation energy of the diatomic molecule in the ground electronic state. We can also find approximate dissociation energy of the molecule, dissociation energy of the molecule in the excited electronic state. This is dissociation energy in the ground electronic state. This is dissociation energy in the excited electronic state. This we can obtain from the electronic spectrum of the diatomic molecule. From the electronic spectrum of diatomic molecule. Very, very important. Birch-Sponer method is an important technique by which we can find, approximate dissociation energy of the molecule in the ground electronic state or approximate dissociation energy of the molecule in the excited electronic state. To find the approximate energy in the excited electronic state, we need electronic spectrum. To find the approximate energy of the molecule, approximate dissociation energy of the molecule in the ground electronic state, we need either IR spectrum or Raman spectrum. So using Birch-Sponer method, we can find this. Now, I am going to discuss how to find the dissociation energy of the molecule in the excited electronic state using Birch-Sponer extrapolation method. See, what I mean here is, listen, what is D0 double prime? You know all these things, but anyway, I'll just explain. What is D0 double prime? Listen, so if a diatomic molecule is given, you know very well, it has electronic state. We represent the electronic state using potential energy diagram like this. Potential energy is plotted against the internuclear distance, and we get the potential energy curve like this for the diatomic molecule. Suppose if this is the ground electronic state, then this is the ground vibration level, V equal to 0. Then we have V1, V2, etc. And there is a maximum where the molecule dissociate. Listen, this gap, that is V0 to, this is called Vmax. This level is called Vmax level. The gap between V0 and Vmax is what we call as D0 double prime. D0 double prime. What is D0 double prime? D0 double prime is nothing but dissociation energy of the molecule in the ground electronic state. This we can get from the IR spectrum, from the results of IR spectrum, or from the IR spectrum or from the Raman spectrum. Clear? What is meant by D0 prime? You also know that in the case of diatomic molecule, we have ground electronic state. But apart from this, we also have excited electronic states. It may be first excited or it may be second excited. Okay, so it is some excited electronic state. Okay, this is an excited electronic state. Now, here also we have V0 level, V1, V2, etc. and there is a Vmax. Vmax. Isn't the gap between V0 and Vmax for an excited electronic state is represented as D0 in wave number unit with a single prime symbol. D0 single prime means this is dissociation energy of the molecule in the excited electronic state. D0 double prime means the dissociation energy of the molecule in the ground electronic state. Okay, this information we can get, D0 double prime we can obtain by using Burgess-Bonner extrapolation method. Okay, from the IR spectrum data or Raman spectrum data. D0 single prime can be obtained by using Burgess-Bonner extrapolation method using the electronic spectrum results. Okay. Suppose for a diatomic molecule, the spectrum is obtained in this manner. Suppose, okay, we get this is called vibrational core structure. Okay, the first line corresponds to 0 to 0 transition. Second line corresponds to 0 to 1 transition. Okay, what is meant by 0 to 0? See, this is ground electronic state and this is some excited electronic state. Maybe first excited or second excited, some excited electronic state. Listen, this is V double prime equal to 0 level. We all know that at room temperature, right, almost 99.9% molecule present in the ground vibrational level of the ground electronic state. I repeat, at room temperature, 99.9% almost all molecules are present in the V double prime 0 level of the ground electronic state. When you pass radiation, what will happen? The molecules present in the V double prime 0 level can undergo excitation. It is get excited. Okay, it may go to V equal to V prime 0 level, or it may go to V prime 1, V prime 2, V prime 3, etc. So V double prime 0 to V single prime 0, it is called 0 to 0 transition. 0 to 0 transition will give a small peak actually, but I have given here as a line. Actually, we should get a peak, a small peak. Okay, then 0 to 1 transition will give another peak with a different intensity. Then 0 to 2 will give another peak. Okay, so this is called vibrational core structure. Like that, different transitions will give different peaks or lines in the spectrum. This is what we call it as vibrational core structure of the diatomic molecule. Vibrational core structure in the electronic spectrum of diatomic molecule. Observe carefully, in this spectrum there is no continuum limit. We are not getting any continuum here. If spectrum is obtained like this, then how to calculate the dissociation energy of the molecule? Okay, for this we are going to use what is called Burgess-Bonner extrapolation method. Okay, observe this carefully. 0 to 1 transition, 0 to 1, yes, 0 to 1 transition is here, and we can find the frequency of the transition from the spectrum. Okay, in the spectrum, the second peak, right, the second peak corresponds to 0 to 1 transition, right? Find the frequency of that peak from the spectrum. Okay, that is nothing but nu bar 1, 0. Okay, and this line The first line corresponds to 0 to 0. Okay, the frequency is represented as nu bar 0, 0. Okay, actually, isn't the second number corresponds to V double prime and the first number corresponds to V single prime. Okay, so nu bar 0, 0 means 0 to 0 transition. Nu bar 1, 0 means 0 to 1 transition. Nu bar 2, 0 means 0 to 2 transition. That's the meaning. Now, observe carefully. If I subtract nu 1, 0, okay, minus nu 0, 0, what will I get? See, nu 1, 0 is nothing but the energy required for the transition 0 to 1 level. Okay, 0 to 1 level. 0 to 1. Nu 0, 0 corresponds to energy required for this transition, 0 to 0 transition. Okay, I have 0 to 1 transition and 0 to 0 transition. If I subtract 0 to 0 transition frequency from the 0 to 1 transition frequency, we can find this gap. This is the gap between 0 and 1 level, okay? Between 0 and 1 level. So, if I subtract 0, 0 from 1, 0, we get the gap, energy gap between 0 and 1 level. Similarly, if I subtract 0, 1, 0 from 0 to 0, we get the gap between 1 and 2 level. V equal to 2 level. This gap we cannot type. Okay, so the gaps, adjacent level gaps, right? The adjacent level gaps between the vibration levels of the excited electronic state can be obtained from the spectrum. So, we can find the energy gap between adjacent levels. We know very well, if I add all the values, we get many values. If I add all the values, yes, I can get D0 single prime value. What is D0 single prime? This is nothing but this value. Okay, if I add the gap between 0 to 1, 1 to 2, 2 to 3, etc., if I add, I'll get D0 single prime value. So, D0 single prime is equal to delta G01 plus delta G02 plus delta G03, etc., It depends on how many lines we get. Okay. But the problem is, we cannot get the complete set of lines. Okay, if we get all the set of lines, yes, we can exactly find out D0 prime. But mathematically this is okay, but experimentally we get only few lines. Based on the few lines that is obtained, how to find the D0 prime? Yes, we can do that. How? Listen, we know very well the gap between adjacent level, the energy gap between adjacent vibrational level is equal to, in the excited state, we represent the excited state with a small prime. Okay, the gap between adjacent vibrational levels in the excited electronic state is equal to omega E bar prime minus 2x E prime omega E prime into V plus 1. Okay, this is the formula. This formula will give the gap between adjacent vibrational levels in the electronic state. And this, since it is excited electronic state, we put prime symbol. Okay. And keep this in mind, this is very important. Always the gap between 0 and 1 will be large. And as we go above and above and above, the gap decreases. Okay, so the energy gap between 0 and 1 level is greater than energy gap between 1 and 2, which is greater than the energy gap between 2 and 3. So as we go above and above, the gap, energy gap decreases, and near Vmax or at the Vmax, it becomes 0. So I can write D0 prime is nothing but sum of all these energy gaps. If I add all the energy gaps, adjacent energy gaps, yes, we can find D0 prime. But it is not that easy because it is very difficult to obtain all the values. Then what to do? Listen, if I plot this delta G versus V, if I plot delta G, the gap, adjacent energy gap between adjacent levels, okay, versus vibrational quantum number V, here V equal to 0, right? Sorry, if I put V equal to 0, I'll get some value for this. Okay, if I put V equal to 0, I'll get some value. Okay, if I put V equal to 1, I'll get some value. and I have minus sign here, so it decreases, the gap decreases, okay. For different V values, we get lines like this. Then listen, after higher vibrational value, what happens is that the gap, it never goes in the linear fashion, it actually decreases like this. It becomes a curve. Okay. What Burge and Spooner did was, they have drawn a straight line using these the lines which are actually exist linearly. No, using those points. Okay, some points forms linear line. So using those lines, he plotted a linear line. Okay, and he extrapolated that line to the x-axis. This is what we call as Burge-Spooner extrapolation. Okay, Burge-Spooner extrapolation, right? The area under this triangle, right? The area under this triangle will give you the sum of all these values. The sum of delta G01 plus, delta G12 plus, delta G23 plus. Okay, so the sum of all the gaps we can obtain by using this. Okay, so this area, the area under this triangle is equal to the D0 single prime, but it is approximate. Why it is approximate? Listen, actually this curve, experimentally this curve goes like this, right? Initially for lower V value, we get linear like points. Okay, the points appear as linear straight line, but after a certain value of V, okay, it takes a curve path. So this is the original curve, experimental values. But what Burge-Spooner did was, they extrapolated these points and they plotted a straight line. Okay, and the area under this triangle, right, is given as D0 single prime, right? But since why it is approximate? Because see this region. Okay, let me draw this region like this. This region, right, it is not experimental actually. Okay, so this much amount of this much area, right, is added to this quantity, which makes this quantity approximate 1. Okay, so D0 prime, which we obtained through Burge-Spooner method, is not accurate. It is approximate. Why it is approximate? This much area is added as extra. Is added as extra in the Burge-Spooner plot. Okay, but finding area is very easy because it is just a triangle. So if you put half into BH, we get the area. But the original area is supposed to be this area. Okay, right? You should go like this, and along the curve we should turn, and we should find out this area. This area will give you the exact D0 prime, but Burge-Spooner method takes some extra area here. Okay, this is actually the error, right? So since this is also included in the area, so D0 prime is not accurate, it is approximate. See here, see this is the ground electronic state, and this is an excited electronic state. This is nothing but dissociation energy of the molecule in the ground electronic state, and this is nothing but dissociation energy of the molecule in the excited electronic state. And this transition is called 0 to 0 transition, and this frequency we can get from the spectrum. Okay, I can get this frequency from the spectrum. Now observe carefully. This D0 prime we got from Burge-Spooner extrapolation, right? From Burge-Spooner extrapolation, we can find D0 prime. Now our goal is to find the D0 double prime. Is it possible? Yes, we can do. How? Listen, observe this graph, observe this picture carefully. Here, the molecule, diatomic molecule, dissociate into atoms in the ground electronic state. Similarly, here also, the molecule is dissociated into atoms. But here, the atoms are in the lower energy, whereas here, the atoms are in the higher energy. Okay, so what does this gap indicate? This gap indicates that it is an excitation energy of the atoms. Okay, atom, right? Here it is in lower energy, and the same atom goes here and become excited. So this atom and this atom, they are one and the same, but the energies are different. So we can say that this energy gap has excitation energy of the atom, which we can obtain from the atomic spectroscopy, right? Depending upon which atom is produced, right? Take the atomic spectrum of that atom. From the atomic spectroscopy, yes, we can find this value. If I know excitation energy, if I know this, if all these three values are available, we can find this one. How? How? Observe carefully. D0 double prime plus this excitation energy. D0 double prime plus this excitation energy, okay, will give me this much energy, right? This gap. This gap is also equal to, see, 0 to 0 prime frequency, that is energy, plus D0 prime, right? 0 to 0 plus D0 prime is equal to D0 double prime plus excitation energy. So I can write D0 double prime plus excitation energy is equal to energy for 0 to 0 transition plus the dissociation energy of the ground electronic state. Yes, I know this from Burgess-Spanner extrapolation. This we can obtain from the electronic spectrum. This we can get from the atomic spectroscopy, atomic spectrum of that atom. If I know all the three values, yes, I can find the dissociation energy of the ground electronic state. Dissociation energy of the molecule in the ground electronic state using this method. Okay, and try to remember all this formula. Okay, take. So the next topic that we are going to discuss under electronic spectroscopy is that rotational fine structure. You all know that in the low resolution spectrometer, if you take the electronic spectrum of a diatomic molecule, right, it appears like a band. Okay, very specifically in the solution state. If you take the same spectrum in high resolution in the gaseous state, okay, or in the high resolution, the band, the single band that we got, it is appear as fingers. Okay, we call this structure as vibrational core structure, and each peak corresponds to some vibrational transition. And we discussed about all these lines and why we got these lines and what is the use of those frequencies. We discussed everything. Now, if I take very high resolution, very high resolution of the electronic spectrum in gas phase of the molecule, suppose the diatomic molecule is present in gas phase, then each of these peaks actually, they consist of many closely spaced lines. Suppose I'll take this particular vibrational transition 0 to 1. I'm sorry, 0 to 0. The 0 to 0 transition, it will normally appear as a peak in low resolution. But if you take the same spectrum in gas phase with high resolution, okay, the peak appears as many lines. Okay, we get branch of lines. Now we need to explain why or what is the reason for getting these lines. Okay, similarly 0 to 1 consists of many branch of lines. 0 to 2 consists of many bunch of lines. So each peak in the vibrational core structure, right, consists of many bunch of lines in the high resolution spectrum of the gas phase molecule. Okay, is this clear to all? Now we need to give explanation for the rotational fine structure. Okay, yes, how to explain. See, first we'll consider energy. Total energy of a molecule in the given electronic state. Observe the words carefully. Total energy of the molecule in a given electronic state is equal to electronic energy plus vibrational energy plus rotational energy under Born-Oppenheimer approximation, right? According to Born-Oppenheimer approximation, right, we can write the total energy of the molecule as electronic plus vibrational plus rotational. Okay, so I keep electronic as such, I keep vibrational energy as such, and rotational energy, f of j can be written as bj into j plus 1. I am giving the energy in wave number unit, okay, so in centimeter inverse. Observe, this is very important. F of j is given as bj into j plus 1. Here, I did not include centrifugal distortion. Why? The reason is, the effect of centrifugal distortion is so small. So we can ignore that. So centrifugal distortion is ignored, right, in this formula. So I am going to use this formula as the energy formula for a molecule in the electronic state. Okay, so this will give the energy. Now, what is the selection rule? Yes, here we use two selection rules actually. First one is delta J plus or minus 1 only. This selection rule is applicable if transition takes place from singlet sigma to singlet sigma. If the ground electronic state is singlet sigma and the excited state also singlet sigma, then for this transition delta J should be plus 1 or minus 1. Okay. For other transitions, right, apart from singlet sigma to singlet sigma, if you take any other transition, then delta J can be 0 or plus or minus 1. Right? And in this, you should be very careful. J0 to J0, because if you say delta J0 means lower level J value, higher level J values are same. Then only you get delta J0. Same means, listen, it can be 2 to 2. It can be 3 to 3. It can be 4 to 4. But it should not be 0 to 0. This is not allowed. J0 to J0 is not allowed. Keep this in mind. Very important. And you know very well, depending upon delta J values. Here delta J, possible delta J values are minus 1, 0 and plus 1. Delta J minus 1 means we call those lines as P branch lines. Delta J0 corresponds to Q branch and delta J plus corresponds to R branch. So in the electronic spectrum, very specifically in the vibrational core structure of electronic spectrum, each vibrational peak consists of bunch of lines, and those lines are actually P, Q and R branch lines. So we get P branch line, Q branch line and R branch line. Okay. Is this clear to all? So now the next goal is, what is the energy required for the transition, also called frequency of the spectral line. At what frequency the rotational lines will appear. Okay. The frequency of the rotational line is equal to change in the electronic energy of the electronic states, change in the vibrational energies of the vibration levels belongs to the electronic states. Okay. Then this is the energy, rotational energy in the higher electronic state, and this is the rotational energy in the lower electronic state. Okay. Listen, the rotational constant values in the ground electronic state and the exit electronic states need not be same. So I represent them as B prime and B double prime. B prime is rotational constant in the exit electronic state. B double prime means rotational constant in the ground electronic state. Okay. And since we are going to focus only on rotational structure, okay, this difference in electronic energy and difference in vibration energy, this sum is represented as nu bar V prime comma V double prime. It corresponds to a particular vibrational transition. It may be 0 to 0 or 0 to 1 or 0 to 2, whatever it is. Okay, I am going to call this as band origin. Band origin. Okay, this frequency corresponds to band origin for that vibrational transition. Okay, so I can represent this as nu bar, and this is simply represented as nu bar v prime comma v double prime plus the rotation energy of the rotation energy in the excited electronic state and rotation energy in the ground electronic state. Okay? Yes. This formula will give the frequency of these rotational lines that appear in the electronic spectrum. Okay? Now listen. So I told you already we get R branch line, P branch line and Q branch line. What is the frequency, right, of R branch line? For R branch, you know very well, for R branch, okay, delta J should be plus 1. What is delta J? Higher J value minus lower J value. J prime minus J double prime is equal to plus 1. Or bring this J double prime to the right hand side. So we get J prime, J single prime equal to J double prime plus 1. Right? Then in this formula, wherever J prime is there, in the place of J prime, we put J double prime plus 1. And if you simplify it, you get a formula like this. Okay? And this is nothing but band origin plus B prime plus B double prime into J double prime plus 1 plus B prime minus B double prime into J double prime plus 1 the whole square, where the J double prime can take 0, 1, 2, 3, etc. Okay? So this gives you the frequency of the R branch line. Frequency, general expression for frequency of the R branch line. Similarly, for P branch, delta J should be minus 1, which means J prime minus J double prime should be minus 1. J prime is higher J value, J double prime is lower electronic state J value. Okay. J prime minus J double prime should give minus 1, or I can write, bring this J double prime to the right hand side and minus 1 to the left hand side. So we can write J double prime equal to J single prime plus 1. Now in the general formula, wherever J double prime is available, you put J single prime plus 1. If I substitute that and if I simplify, we get an expression like this. So frequency of the P branch equal to band origin minus B prime plus B double prime J prime plus 1 plus B prime minus B double prime J prime plus 1 the whole square. Okay, so this will give you the frequency of the P branch line. And what are the allowed values of J prime here? J prime can take value 0, 1, 2 like J double prime here. Now you just see these two formulas. Observe carefully. I have B prime minus B double prime. Here also I have B prime minus B double prime. I have plus sign. Here also I have plus sign. And here I have B prime plus B prime. Here also I have B prime plus B prime. But in R branch I have plus sign, and in P branch I have minus sign. Okay. Now what I am going to do? I am going to write this equation in a simple manner. Okay. Instead of writing J prime, J double prime, I will write in a simplified manner. So what I am going to do? Listen. Let me write in the next page. So this, listen, we can combine, listen, or in a simplified form, we can write the frequency of the P branch and R branch line. Right? This is the formula. The formula is this. Listen, I just replaced J double prime plus 1 and J single prime plus 1 in the P branch and R branch line equations, and I replaced that by number m. Okay, some value m. Okay, right? And here I put plus, here also I put plus. Observe carefully. But you know very well, for R branch, we should get plus here. For P branch, we should get minus here. Right? But what about the values of m? Listen, if m values are positive, then it corresponds to R branch line. If m values are negative, it corresponds to P branch line. That's all. Very simple. Right? And what are the allowed values of m? Plus 1, plus 2, plus 3. M cannot be 0. What are the allowed values of m for a P branch? Minus 1, minus 2, minus 3, etc. What about the Q branch? For Q branch, delta J should be 0. Delta J 0 means J prime minus J double prime equal to 0. or I can say J prime and J double prime are equal. Okay, I'll write like this. J prime and J double prime are one and the same. Right. So lower J value and higher J value is supposed to be same, but keep this in mind. As per selection rule, if lower J is 0 and higher J is 0, this transition is not allowed. Okay, there is a restriction in the selection rule. Right. Other transition, J double prime 1 to 1, 2 to 2, 3 to 3, all other transitions are allowed. Clear? Therefore, I can write. So in the original formula, this is the general form. In this general formula, wherever J prime is there, you put J double prime. If I put J double prime and if you simplify, we get an equation like this for Q branch. This is for Q branch. For Q branch, we get the band origin plus B prime minus B double prime J double prime plus B prime minus B double prime into J double prime square. Okay, remember J double prime cannot be 0. Why? If J double prime is 0, then 0 to 0 become allowed. But J double prime 0 is not allowed. Therefore, observe carefully. Since this is not allowed, we do not get Q branch line at the band origin. Okay, so Q branch lines do not appear at the band origin. Okay, this is very important. See, we all know that if you take a vibrational transition, one particular say 0 to 0 or 0 to 1 or 0 to 2 in the electronic spectrum, you take any one vibrational transition, okay, and say this is the band origin. Suppose this is band origin, where we get, see, frequency increases from left to right, where we get P branch and where we get R branch. Remember, in the higher frequency side of band origin, we get R branch line. These are all R branch lines. In the lower frequency side of band origin, we get P branch lines. And Q branch lines will appear, usually it will appear close to the band origin. Okay, in some molecule it will appear in the lower side, in some molecule it will appear in the higher side of band origin. It depends. Okay, we all know that in molecule, listen, in some molecule the ground electronic state, okay, this is the internuclear separation. Let me take this as R. This is the internuclear separation for the ground electronic state. Okay, this is ground electronic state. We will put R naught, and this is energy. And the excited electronic state may also have the same R. So the internuclear distance for the ground electronic state and the internuclear distance for the excited electronic state, excited electronic state are equal. Suppose if the ground electronic state internuclear distance and the excited electronic state internuclear distance are exactly same. Okay, R equal to R excited. In this case, the spectrum will appear like this. How? The 0 to 0 transition will appear with high intensity. 0 to 0 appear with high intensity. Okay, then 0 to 1, then 0 to 2, like that we get spectrum. And in this case, listen, the rotational constant in the lower electronic state, B double prime, and the rotational constant in the excited electronic state, since internuclear distance are same, okay, these values are almost equal. Okay, number 2. Suppose in another molecule, okay, observe carefully, in another molecule we have ground electronic state here, with the internuclear distance R naught, and we have an excited electronic state with internuclear distance R. See, R. In this case, R is greater than R naught. Okay. If internuclear distance of the ground electronic state and exit electronic state are not equal, then we get spectrum like this. In this case, 0 to 0 will appear with lower intensity, then 0 to 1, 0 to 2. Some transition will appear with high intensity. It need not be 0 to 4 or 0 to 5. It can be anything. Okay. The point here is 0 to 0 is not the high intense line. Okay. So if I get spectrum like this, we can very easily say that ground electronic state internuclear distance, exit electronic state internuclear distance are almost equal. If you get spectrum like this, then the internuclear distances are not equal. Right? Is this point clear? In this case, observe carefully, in this case, listen, the ground electronic state has lower internuclear distance. Therefore, the rotational constant for the ground electronic state is higher. Right? And for the exit electronic state, the internuclear distance is large. Internuclear distance large means the corresponding rotational constant is small. Okay. So, in diatomic molecule, having this type of electronic arrangement or electronic state, okay, B double prime is greater than B prime is possible. Now, we have, I'll just show you one more case here, third case. In some molecule, this situation also may happen. What is that? Listen, what is that? See, this is the ground electronic state. Sometime the excited electronic state may appear like this. Now, in this case, see, R naught, right, internuclear distance for the ground electronic state, and this is internuclear distance for the exit electronic state. If we compare R naught and R naught is greater than R now. In this case also the spectrum appear like this, that is 0 to 0 transition appear with less intensity, then 0 to 1, 0 to 2, 0 to 3, 0 to 4, some line will appear with a high intensity. We get spectrum like this. Right? So, remember, if the internuclear distance of the excited electronic state and the ground electronic state are different, it may be higher or lower, we get spectrum, right, of this type. Now, see, in this case, the internuclear distance for the excited state is small compared to the ground electronic state. So, in this case, B value in the exit electronic state and the ground electronic state and the B value in the exit electronic state, if we compare, yes, B value in the exit electronic state is large. Why I am saying this is that people normally think that the B value in the higher levels are lower in general, but it is not so. Within an electronic state, see, within a given electronic state, as you move to the higher vibration level, yes, rotational constant will decrease. But now we are comparing rotational constant of the ground electronic state with the rotational constant of the exit electronic state. Okay, they are not same, right? Here there are two situations possible. B double prime may be less than B prime, or B double prime may be greater than B prime. Two situations are possible. And one more situation, that is B prime and B double prime are approximately equal, that is also possible, but it is a rare case. That one is a rare case. Okay, so there are three situations, right? Yes, theoretically speaking, there are three situations. What are they? Number one, B single double prime and B single prime may be approximately equal. This is actually a rare situation. Number two, B double prime may be greater than B single prime. Number three, B double prime may be less than B single prime. So there are three cases possible. Now what I am going to do, for these two cases, how the spectrum is supposed to look like. Okay, how the rotational fine structure look like. Yes, we'll discuss that. If suppose B prime is less than B double prime, then how the rotational fine structure exists in the vibrational transition of the electronic spectrum. Okay, if B prime is less than B double prime, then B prime minus B double prime should be negative. we all know that the frequency of the R branch line, yes, this is the general formula for frequency of the R branch line. Okay, here m square is there, so whether m is positive or negative, m square is always positive. But for R branch, you know very well, m should be positive only. M should be positive value only. Now, observe this carefully. Listen. Generally, R branch lines appear in the higher frequency side of the band origin. Okay, now here I have plus. Here B prime minus B double prime is negative. This is negative. Okay, see, this quantity is negative. Therefore negative, and here I have plus. Plus into minus become minus. Now as m increases, here I have m, here I have m square. So as m increases, what will happen? Since this is a negative quantity, as m increases, the line starts to appear closely. So as m increases, line spacing decreases. The line starts to appear closer. What will happen? At one particular frequency, the line stops. R branch line, this is R branch. R branch line stops. Then if m increases further, the R branch line starts to return. Okay, it returns and goes in the lower frequency side. Okay, this is what happened in the R branch side if B prime is less than B double prime. And the frequency where R branch line stops, okay, this is called the band head. Band head. Okay, suppose if you plot this is something like this, then it look like a band. And this is the band head, and this is called tail. Okay, tail of the band. Okay, the tail is degraded towards the lower frequency. Okay, so where the band head appears, the band head appears at the higher frequency side. At the higher frequency, the band head appears at the higher frequency side. And where the degradation occurs, band is degraded towards, listen, higher frequency means violet region. Degradation occurs in the opposite side. Lower frequency means red region. So band is degraded towards red. Okay. So when B prime is less than B double prime, the band appears in the R branch. Okay. We get a band. Band appears right in the R branch. Right. How it will appear? We get band head at higher frequency side. This is band head and this is called degradation. This side is called degradation. So band head appears at higher frequency side and degradation of the band appears, it occurs towards lower frequency side, also called red region. Okay. Keep this point in mind. This is very important. If B prime is less than B double prime, we get band. Okay, we get a band at the R branch side. Right, we get a band head and we get what is called a tail. Tail or degradation, right? The band degradation occur in the towards lower frequency side, also called red side, red region. Okay, now this is in the R branch. What happens in the P branch and Q branch? Yes, let me explain this.
Sir, last page one.
Yes, this is the general expression for P branch. Okay, general expression. Now, listen. B prime minus B double prime is negative. We all know that P branch lines usually appear in the lower frequency side of the band origin. Right? Suppose if this is the band origin, R branch will appear in the higher frequency side. Frequency increases from left to right. R branch line appears in the higher frequency side. P branch appear in the lower frequency side. As m increases, since this is negative, what will happen? the P branch line starts to appear in very low frequency. So what happens is that the gap increases. The gap increases and it goes like this. Right? So if B prime is less than, see, don't forget, if B prime is less than B double prime, then B prime minus B double prime is negative. If this is negative, as M increases, the gap between the adjacent line in P branch increases. So as M increases, line spacing increases in the lower frequency side. Okay, this is for P branch. What about Q branch? For Q branch, yes, this is the general formula for Q branch, right? And B prime is less than B double prime. We have taken this case. Okay, B single prime is less than B double prime. Therefore, B single prime minus B double prime is negative. Yes, this quantity is negative. This is also negative. Since both are negative, and what are the allowed value of J double prime? 0 is not allowed. 1, 2, 3, 4 and all allowed. So if you put J double prime 1, 2, 3, listen, since these two are negative, this is band origin. Since these two are negative, Q branch lines will appear in the lower frequency side of band origin. Okay, so this is band origin. If molecule in which B prime less than B double prime, then Q branch lines will appear in the lower frequency side. The lower frequency side of band origin. This is called Q branch. Usually, resolving the Q branch lines is a very tough task. Okay, for small values of J double prime, their lines will appear very closely. It is very difficult to resolve them. Okay, yes, keep this in mind. Yeah, in some diatomic molecule, B prime may be greater than B double prime. This may also occur. If B prime is greater than B double prime, then B prime minus B double prime is positive. If this is positive, what will happen in the R branch side, P branch side and Q branch side, we'll discuss. First, I'll take P branch. Okay, so what will happen to the frequency of the P branch lines? Listen, you know very well. I'm sorry, first I'll take R branch. Frequency of the R branch, right? Yes, what is the formula? Band origin, okay, B prime, B double prime, band origin, plus we have the formula that is B prime plus B double prime into M, then plus B prime minus B double prime into M square. Okay, this is the formula. And here see, B prime minus B double prime is positive now. So this is positive. Since this is positive, as M increases, okay, the line spacing increases. So in this case, see, as M increases, okay, line spacing increases. So we do not get any band in the R branch side. No band in the R branch. Okay, we do not get, because line spacing increases, so we get some kind of degradation, right? Okay, line spacing increases, that's all. What will happen in the P branch? See, in the case of B prime greater than B double prime, right? What is the frequency of the P branch line? General formula, band origin. This is band origin plus B prime plus B double prime into M plus B prime minus B double prime into M square. This is the same formula we should use. Okay, for R branch, M values are positive, plus 1, plus 2, plus 3, etc. For P branch, M values are negative, minus 1, minus 2, minus 3, etc. M values are negative here. Now observe carefully, B prime minus B double prime is positive. So this is a positive quantity now. Right? But what about M? M is negative. Now listen carefully. If I put M negative number, M negative, okay, so this is negative, whereas here this is positive. So what will happen? right, in the p branch side, as m increases, listen carefully, as m increases, right, one second. So in this case, what will happen, listen, as m increases, right, the lines in the p branch side, right, they starts to appear, right, with a lesser gap, right. So here, as m increases, right, the line spacing decreases. Line spacing decreases, and we get a band head. We get a band in the p branch side. Okay, right. So we get a band head. Let me write in the next page. We get a band head, and we get a degradation in the higher frequency side. Right. I'll take it later. Yes. So now what will happen? Listen. As m increases, we get a band head. Band head appears in the higher frequency side. Appears in the in the lower frequency side. In the lower frequency side, okay, and the band degradation, right, occurs towards, band is degraded towards higher frequency region called violet. So we get a band degradation in the violet region, and we get band head in the lower frequency side or red region. Okay, take it. So in some molecule we get a band in the R branch side. In some other molecule we get band in the P branch side. When we get band in the R branch side and when we get band in the P branch side, that depends upon the molecule. Okay, if B prime, B double prime values are given, yes, we can compare. We can compare and we can give the explanation. Right? Take note. Listen, this is normal. Suppose I'll take 0 to 0 transition. Right? We usually show that we get a peak for 0 to 0, but the peak appear either like this or like this. Okay, so we may get band head in the higher frequency side, and the degradation occur in the lower frequency side. It is called violet degradation. I'm sorry, it is called red degradation. Degradation occur in the lower frequency. When it will appear? This appears if B prime is less than B double prime. If B prime is greater than B double prime, in this case, okay, and listen, this band appears in the R branch. Whereas when B prime greater than B double prime, the band appears in the P branch. P branch, and we get band head in the P branch, okay, and degradation occurs towards higher frequency, right? So it is called violet region. Degradation occurs in the violet region, whereas here degradation occurs in the red region. Band head appears in the higher frequency side. Here band head appears in the lower frequency side. Here band head appears in the R branch. Here band head appears in the P branch. Is this clear to all? See, Q branch, what is the formula? A nu bar band origin B prime B double prime plus B single prime minus B double prime into J double prime plus B single prime minus B double prime into J double prime square. Correct? Now listen, for this case, B prime is greater than B double prime, so this is positive. This is also positive. If both are positive, listen, if both are positive, as J double prime increases, where we will get Q branch? Whether it is lower than, whether it will appear in the lower side of, yes. If this is the band origin, this is band origin, then since these values are positive, Q branch lines will appear in the higher frequency side of band origin. Correct? So for this case, Q branch will appear in the higher frequency side. For this case, Q branch will appear in the lower frequency side. So these are all the informations we get from the spectrum, right? Parabola, it is called 4-trot parabola, 4-trot. Okay, 4-trot diagram or parabola. 4-trot parabola. What is meant by this? Listen, suppose I'll take this case, that is P prime less than B double prime. I'll take this case. Suppose in a diatomic molecule, B prime is less than B double prime. In this case, listen, now if I plot frequency in the x-axis and m values in the y-axis, m values. Here m value 0 and here m values are positive, I am plotting m. And below m values are negative. Okay? Observe carefully. It's very, very, very important. Right? For R branch, let me write here. Frequency of the R branch equal to band origin B prime B double prime plus B prime plus B double prime into M plus B prime minus B double prime B single prime B double prime M square. Okay, this is the formula for R branch. First I'll take R branch. Okay, in R branch you know very well M values are positive, plus 1, plus 2, plus 3, etc. M value positive means we get curve above the above this x-axis. Okay, because above x-axis M values are positive. Right? Listen, M cannot be 0. M cannot be 0. M starts from plus 1, plus 2, plus 3, etc. If I put M plus 1, if I put, see, suppose, assume that this is the band origin. Okay, this frequency corresponds to band origin B prime, comma B double prime. This is the band origin. Right? Actually, it does not start from band origin, it starts little above. So what will happen? As M increases, right? See, this is band origin. As M increases, R branch line starts to appear in the higher frequency side. Higher frequency side of band origin. Okay? Right? What will happen? The gap decreases, then it stops at a particular frequency, then it returns. So the peak, the parabola is supposed to go like this. It looks like a, so this is the parabola. This parabola goes like this. This is for R branch. R branch. Okay. Now, what about for Q branch? P branch. In the case of P branch, right, we get the same formula, V prime comma B double prime plus B single prime plus B double prime into M plus B prime minus B double prime into M square. And what are the allowed values of M? Minus 1, minus 2, minus 3, etc. So here M values are negative. Right? Now, in this case, as M increases, okay, P branch gap increases and it goes like this. It keep on goes like this. Right? And you know very well Q branch. Where Q branch will appear? Q branch will appear in the lower frequency side of band origin. So Q branch will go like this. This is P branch and this is Q branch and this is R branch. So we get a band. We get a band in the R branch side. Okay. If I differentiate this M, if I differentiate M with respect to d nu, if I put this value equal to 0, yes, I can find at what frequency we get the band head. At what frequency we get the band head. Yes, we can do this. I am going to give you the final expression directly. The frequency of the band head is equal to, just note down, this is the formula. And these parabola are called 4-trot parabola. Okay. From the 4-trot parabola, we can find the frequency at which the band head appears. Okay, the frequency at which band head appears. Let me give the value directly. So the formula is that we get band head equal to B single prime plus B double prime minus sign. okay, divided by 2 times B single prime minus B double prime. Use this formula to calculate the frequency of the band head that appears in the R band side. Okay, take care.